These are the answers to the AP Chemistry packet that covers topics 7.6 to 7.10. On this slide, you can see Unit 7 at a glance. Unit 7 is entitled Equilibrium. In this video, we will take a look at topic 7.6, Properties of the Equilibrium Constant, topic 7.7, Calculating Equilibrium Concentrations, topic 7.8, Representations of Equilibrium, topic 7.9, Introduction to Le Châtelier's Principle, and topic 7.10, Reaction Quotient and Le Châtelier's Principle. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 7.6, Properties of the Equilibrium Constant. Here are some essential knowledge statements from the AP Chemistry course and exam description. The letter K refers to the value of the equilibrium constant. When a reaction is reversed, K for the reversed equation is equal to the reciprocal of the original K. When the stoichiometric coefficients of a reaction are multiplied by a factor, n, K for the modified equation is equal to the original K raised to the power n. When reactions are added together, the K of the resulting overall reaction is the product of the individual K values for the reactions that were added together. Since the expressions for the equilibrium constant K and the reaction quotient Q have identical mathematical forms, all valid algebraic manipulations of K also apply to Q. Question 1. Fill in the missing information in the table below. Write the modification that was made to the equation shown above and calculate the new value of Kc. So the original equation that is shown at the top of this slide is H2 plus I2 to produce 2HI, and the value of Kc for that equation is 51. Our first example shows 2HI produces H2 plus I2, so we can see that the modification that was made to the original equation shown above is that the equation has been reversed. When a reaction is reversed, K for the reversed equation is equal to the reciprocal of the original K. So here is what the original equation looks like with its equilibrium constant expression. Here is the reversed equation, so we can see that the equilibrium constant expression has been flipped upside down. So 1 divided by 51 is going to be our new version of K. 1 divided by 51 is 0.0196. If we round this off to two significant figures, it would be 0.020. Now, for our next equation, it's 1/2 H2 plus 1/2 I2 to produce HI. So the original equation, all of the coefficients have been multiplied by 1/2. That means that the K for the modified equation is equal to the original K raised to the power, in this case, 1/2. So 51 raised to the 1/2 power is going to be the math that we do to calculate the new value of K. Here you can see that when the equation is multiplied by 1/2, the original equilibrium constant expression is raised to the 1/2 power. So 51 to the 1/2 power is the square root of 51, which is 7.141, and we'll round that off to two significant figures, 7.1. In our next equation, 2H2 plus 2I2 to produce 4HI, each of the coefficients has been multiplied by 2. So we're going to go ahead and raise 51 to the second power, or 51 squared. So there's the original equation with the equilibrium constant expression. The new equilibrium constant expression has been raised to the power 2, or squared. So 51 squared is 2,601. If we round that off to two significant figures, it would be 2,600. And now the last modification is HI produces 1/2 H2 plus 1/2 I2. That means that the original equation was both reversed and multiplied by 1/2. So we have to take the reciprocal of 51, and we also have to raise it to the 1/2 power. So the new version of the equation is the original equation reversed or flipped upside down and also raised to the 1/2 power. So 1 over 51 to the 1/2 power, or 1 over the square root of 51, is equal to 0.140. So I'll say 0.14. So those four answers, 0.020, 7.1, 2600, and 0.14, those are the new values of K based on the various modifications that were made to the original equation shown above. Question 2. 3 chemical equations are listed in the table above. In the space below, show how equations number 1 and number 2 can be combined in a certain way in order to produce equation number 3. Calculate the equilibrium constant Kc for equation number 3. So the first thing I'm going to do is focus on equation number 3, and I'll start with the first reactant that I see. So the first reactant is 1 mole of FeF2 solid. And I see that particular chemical in equation 1. It's got the same coefficient, and it's also featured as a reactant, therefore no changes have to be made to equation 1, so leave equation 1 unchanged. Now the next reactant that I see in equation 3 is 2 moles of H+, featured as a reactant. In equation 2, I see 1 mole of H+, and it's featured as a product. So in order to get 2 moles of H+ on the left side of the equation, on the reactant side, equation number 2 needs to be reversed as well as multiplied by 2. So as I do that, H+ and F- will now be on the left, and they will have coefficients of 2, and HF will be on the right, also with a coefficient of 2. When these two equations are now added together, I see 2F- on the left and 2F- on the right, so I can cross those species out on both sides of the equation because they're identical. And when I add these two equations together, I will get FeF2 plus 2H plus to produce Fe2 plus 2HF. It's exactly what equation 3 looks like. So now all I have left to do is determine what mathematical manipulations need to be made to the equilibrium constants for equations 1 and 2 so they can be combined together correctly to produce the value of Kc for equation 3. So equation number 1 was not changed at all. So therefore it has the same value for the equilibrium constant of 2.4 times 10 to the negative 6. Equation number 2, because it was reversed, that means it would be the reciprocal, so 1 divided by 6.8 times 10 to the negative 4, but it was also doubled. Each coefficient was multiplied by 2. That means we have to raise that to the power 2, or make it squared. We're doing both of those changes at the same time. So the new value of Kc for equation 2, with that modification of being reversed and doubled, is it will be 1 divided by 6.8 times 10 to the negative 4 squared. So when we do that math of 1 divided by 6.8 times 10 to the negative 4 squared, we get 2.2 times 10 to the 6, and that is the new version of Kc for equation 2 after the modification has been made. Now, the next step is to combine these two equations together to produce equation 3. So what I'm showing on this slide are all of the equilibrium constant expressions for the original equations, and now the equilibrium constant expressions for the modified version of equation 2, and of course the overall equation 3. So look at what happens if we take the equilibrium constant expression for equation 1 and we multiply by the modified version of the equilibrium constant expression for equation 2. If we multiply those two expressions together, it will equal the equilibrium constant expression for equation 3. That just reminds you that we have to multiply these two values of Kc. So 2.4 times 10 to the negative 6 is multiplied by 2.2 times 10 to the 6. When we do that math, we get an answer of 5.3. So the correct answer for the Kc for equation 3 is 5.3. Remember that in the essential knowledge statements for topic 7.6, it said when reactions are added together, the K of the resulting overall reaction is the product of the individual K values for the reactions that were added together. So 2.4 times 10 to the negative 6 times 2.2 times 10 to the 6 equals 5.3, and 5.3 is the value of Kc for equation 3. Okay, now it is time to take a look at our next topic. This is topic 7.7, calculating equilibrium concentrations. Here are some essential knowledge statements from the AP Chemistry course and exam description. The concentrations or partial pressures of species at equilibrium can be predicted given the balanced reaction, initial concentrations, and the appropriate equilibrium constant K. When the reaction quotient Q is less than the equilibrium constant K, the reaction will proceed with a net consumption of reactants and generation of products. On the other hand, when the reaction quotient Q is greater than the equilibrium constant K, the reaction will proceed with a net consumption of products and a generation of reactants. And finally, when the reaction quotient Q is equal to the equilibrium constant K, the system is at dynamic equilibrium. Both forward and reverse reactions proceed at the same rate, and the proportion of reactants and products remain constant. Now, in the next section of the packet, we have questions 3 through 5, and they are all related to the system represented by the equation shown above, in which 1 mole of hydrogen gas reacts with 1 mole of iodine gas to produce 2 moles of hydrogen iodide gas, and at a temperature of 448 degrees Celsius, the value of the equilibrium constant, Kc, is equal to 51. What you're going to see as a strategy in questions 3 through 5 is the same strategy that was introduced in an earlier video for topic 7.4, calculating the equilibrium constant, and that is to create what is known as a Rice table. So you're going to see a Rice table featured as a strategy in questions 3 through 5. Samples of hydrogen and iodine were added to a previously evacuated reaction vessel. The initial values for the concentrations of hydrogen and iodine were each equal to 2.00 molar. Now let's go ahead and make our Rice table. So there's the reaction, and the initial concentration of hydrogen and iodine were each 2.00 molar. There was no hydrogen iodide present at time 0. Let's go ahead and fill in a value of 0 molar for the concentration of hydrogen iodide initially. Now, the reaction was allowed to proceed at 448 degrees Celsius until the system reached equilibrium. Calculate the concentrations of all 3 gases in the reaction vessel at equilibrium. Since we start this reaction without any hydrogen iodide, the product, we know that the reaction must proceed from left to right, from reactants to products, because there aren't any products to begin with at time 0. So the reaction must proceed from left to right. That means that as this system reaches equilibrium, the concentration of hydrogen must decrease. Obviously, the concentration of iodine, which is also a reactant, must decrease, and then the concentration of hydrogen iodide must increase as the system approaches equilibrium. Now, for the change, since we don't know the number, we're going to use change in terms of x. So for the change in hydrogen, it's going to be minus x. And for the change in iodine, it's going to be minus x. And for the change in hydrogen iodide, it's going to be plus 2x. So remember that when you are filling in the information in the change row of the Rice table, the change in the amount of each substance in concentration or in pressure should be proportional to the coefficients in the balanced equation. So because the coefficients from left to right are 1, 1, and 2, it makes sense that the magnitude of the change is x, x, and 2x. So at equilibrium, the concentration of hydrogen is 2 minus x. Concentration of iodine at equilibrium is also 2 minus x. And the concentration of hydrogen iodide at equilibrium is equal to 2x. So now that we have filled in our rice table as much as we can, the next step in the process is to solve for x. So how we do that is we plug in the values for concentration of hydrogen, iodine, and hydrogen iodide in terms of x into the equilibrium constant expression, which will be concentration of hydrogen iodide squared divided by the product of the concentration of hydrogen times the concentration of iodine. So here we go. On the top, it's going to be 2x squared, and on the bottom, it's going to be 2 minus x times 2 minus x. Since we know the value of the equilibrium constant, Kc, that's 51, we can set this expression equal to 51. Now, all we have to do is solve for x. And before you get a little bit intimidated or concerned about the complexity of this equation, let's take a look at some feature of this expression that allows us to simplify the process of solving for x. And that is, if you look carefully on the numerator and denominator, you will notice that they are both perfect squares. So because this expression happens to be a perfect square, then we can take the square root of both sides of the equation, and that really will simplify the process of solving for x. All right, here we go. The square root of this expression is equal to the square root of 51. So now that becomes on the top 2x, on the bottom 2 minus x, and that is equal to the square root of 51, which is 7.1414. I'm not going to round off the square root of 51 too much, so I've got a few extra decimal places since I want to make sure that I don't round off too early in the process of solving this equation. My next step is to multiply both sides of this equation by the quantity 2 minus x. Now I'm going to distribute by multiplying 7.1414 times 2, and then multiplying 7.1414 times negative x. So when I do that, I get 2x equals 14.2828 minus 7.1414x. My next step in the process is to combine like terms. So I'll add 7.1414x to both sides. Now I have one more step, which is to solve for x by dividing both sides of this equation by 9.1414. And when I do that, I get that x is equal to 1.56. Now that I know that the value of x is equal to 1.56, I can go back to my rice table, plug in the value for x, x, and 2x into the change row of the table like this. So minus 1.56, minus 1.56, and plus 3.12. When I do the math from top to bottom, either subtracting or adding as appropriate, I get 2 minus 1.56, which is 0.44. I do that again for iodine, and then I get 3.12 for my final concentration of hydrogen iodide. Now, just to verify, just to make sure that these three numbers for the concentration of reactants and products at equilibrium actually represents an equilibrium system, let's take these three numbers and plug them in to the equilibrium constant expression. What I'm hoping for is a number that is pretty close to 51 to show that this would represent an equilibrium system. So I have 3.12 squared divided by the product of 0.44 times 0.44. And when I do this math on my calculator, I get 50.3, which is close enough to 51 that I'm satisfied that this is an equilibrium system. All right, now moving on to question 4. So remember that questions 3, 4, and 5 in this packet all deal with the same equilibrium system. Question 4 says, a sample of hydrogen iodide was added to a previously evacuated reaction vessel with an initial concentration of 6.00 molar for hydrogen iodide. Let me go ahead and make the rice table, and we'll fill in a concentration of 6.00 molar for hydrogen iodide initially. The reaction was allowed to proceed at 448 degrees Celsius until the system reached equilibrium. Calculate the concentrations of all three gases in the reaction vessel at equilibrium. So unlike question 3, where we started with a sample of hydrogen and iodine and no hydrogen iodide at all, this is sort of the reverse situation. We're starting with only hydrogen iodide and no hydrogen or iodine present initially. So I'll go ahead and fill in 0 molar for the concentration of the reactants, hydrogen and iodine. As the system approaches equilibrium, it must proceed from right to left, from products to reactants as the system approaches equilibrium. So the concentration of hydrogen must increase, the concentration of iodine must also increase, and the concentration of hydrogen iodide must decrease as the system approaches equilibrium. So remember that the change row of the rice table must be proportional to the coefficients, and the coefficients from left to right are 1, 1, and 2. And we know that hydrogen is going to increase, so it's going to be plus X. Iodine is also going to increase, so plus X. Hydrogen iodide is going to decrease, so minus 2X. So X, X, and 2X, that's the magnitude of the change according to the coefficients of 1, 1, and 2. At equilibrium, we will have a concentration of hydrogen of X. At equilibrium, we have a concentration of iodine that is also X. At equilibrium, we will have a concentration for hydrogen iodide of 6 minus 2X. Now we're going to proceed to a very similar strategy for solving for X. We take the information in the final row of the rice table and we plug those numbers, well, those values in terms of X, into the equilibrium constant expression. So there's our equilibrium constant expression, which is concentration of hydrogen iodide squared divided by the product of the concentration of hydrogen times the concentration of iodine. So it's going to be 6 minus 2X, quantity squared on the top, and X times X on the bottom. Just like in question 3, we're going to set this equal to the Kc, which is 51. Just like in question 3, this expression, even though it might look a little bit intimidating at first, is in fact another example of a perfect square. So all we have to do now to solve for X is to take the square root of both sides of this equation to simplify our math and then do simple algebra from that point on. So here we go. When I take the square root of both sides, I get 6 minus 2X on the top, X on the bottom, and that is equal to the square root of 51, which is 7.1414. I will multiply both sides by X. I will combine like terms. And then when I do that, I get X is equal to 6 divided by 9.1414. So when I solve for X, I discover that X is equal to 0.66. Now that I know that X is equal to 0.66, I can fill in the change row of this rice table with actual numbers. So 0.66 and 1.32 appropriately. That means that at equilibrium, the concentration of hydrogen will be 0.66 molar. Concentration of iodine will be the same value, 0.66 molar. And 6 minus 1.32 is equal to 4.68. So those three numbers are the concentrations for the reactants and the products. To verify that this is in fact an equilibrium system, let's plug in these values for the equilibrium concentrations of reactants and products into the equilibrium constant expression. So 4.68 squared divided by the product of 0.66 times 0.66. I'm hoping for a number that is close to 51, and 50.3. That's close enough so that, yes, I am satisfied that this would represent an equilibrium system. Now, moving on to question 5. Now, what makes question 5 similar to questions 3 and 4 in the packet is that we're still dealing with the same equilibrium system involving hydrogen, iodine, and hydrogen iodide. But what makes question 5 different than questions 3 and 4 in the packet is that instead of starting with just reactants and no products, or starting with just products and no reactants, here in question 5, as you can see, it says samples of hydrogen, iodine, and hydrogen iodide were added to a previously evacuated rigid reaction vessel at 448 degrees Celsius with initial concentrations of the following. So now that we have concentrations for both reactants and products, we're going to have to do a system that I taught you in an earlier video for topic 7.4, which had to do with comparing Q versus K. If we don't compare Q versus K, then we won't know for certain whether the reaction will proceed from left to right or whether the reaction will proceed from right to left as it approaches equilibrium. So why do we do Q versus K? Because it will help us determine in which direction the reaction will proceed as it approaches equilibrium. And that's very important for filling in the rice table with the appropriate plus or minus signs for the change row of the rice table. So in part A, it's going to be Q versus K. In which direction? Toward the left, reactants, or toward the right, products, should the reaction proceed in order to achieve equilibrium? Justify your answer by comparing the value of the reaction quotient, Q, with the value of the equilibrium constant, Kc, which is 51, at 448 degrees Celsius. So how do we calculate Q? It looks identical to the equilibrium constant expression, but this time we plug in the values for this point in time, which is the initial concentrations. So we're not going to get 51 because these are the initial concentrations before equilibrium has been achieved. So for hydrogen iodide, that's going to be 6 molar on the top, so 6 squared. And on the bottom, it's going to be 2 molar for each reactant, so 2 times 2. 6 squared divided by the product of 2 times 2, that's going to be 36 over 4, which is 9. Let's compare the value of 9 with the value of 51, and we can see that since Q is less than K, this means that there are either too many reactants or not enough products. A net conversion from left to right, from reactants to products, will occur until eventually equilibrium is achieved and Q equals K. So now that we know that we're going to go from left to right because Q, 9, is less than K, 51. Again, it appears that there are either too many reactants or not enough products. In order for the value of Q to increase, the forward reaction from left to right, from reactants to products, will proceed until eventually the value of Q will be equal to K at equilibrium. So now that we know that, in our rice table, we can fill in the change with the appropriate plus and minus signs. So initial concentration for hydrogen is 2.00 molar. Initial concentration for iodine is also 2.00 molar. Initial concentration for hydrogen iodide is 6.00 molar. And in the upper right corner of this slide, you can see that mnemonic device where you put, in alphabetical order, you put K before Q. You show the inequality symbol, which is that Q is less than K, because 9 is less than 51, and that inequality symbol is like an arrow. It points from left to right, indicating that the reaction will proceed from reactants to products to achieve equilibrium. So the concentration of hydrogen will decrease, the concentration of iodine will also decrease, and the concentration of hydrogen iodide will increase as the system approaches equilibrium. So it's going to be minus X for hydrogen, minus X for iodine, and plus 2X for hydrogen iodide. Let's go ahead and carry it down. 2 minus X for hydrogen at equilibrium, 2 minus X for iodine in equilibrium, and 6 plus 2X for hydrogen iodide at equilibrium. This process is now very similar to what we did to solve questions 3 and questions 4 in the packet. So this next step in the process is that now that the equilibrium row of the rice table has been filled in with numbers in terms of X, we can plug those expressions in to the equilibrium constant expression and then eventually solve for X. So on the top, it's going to be 6 plus 2X quantity squared, and on the bottom, it's going to be 2 minus X times 2 minus X. We set this equal to Kc, which is 51. Let's hope, and I think you can see it on the slide here, that just like in question 3 and question 4, we don't have complicated math to worry about because this expression is also a perfect square like you have seen before in questions 3 and 4. So we first start off by taking the square root of both sides to simplify that algebra. And when we do that, we get 6 plus 2X on the top and 2 minus X on the bottom. And that is equal to the square root of 51, which is 7.1414. Now I will multiply both sides of the equation by the quantity 2 minus X. Then I will distribute on the right side of the equation by taking 7.1414 and multiplying by both 2 and negative X. Then I will combine like terms in terms of X, and I will simplify if I can. So I'm going to add 7.1414X to both sides, and I will subtract the number 6 from both sides. So now I get 9.1414X on the left and 8.2828 on the right. Last step, solve for X, which would be 8.2828 divided by 9.1414. When I do that math, I discover that X is equal to 0.91. Now that I know that the value of X is equal to 0.91, I go back to my rice table, fill in the change row of the rice table with actual numbers, so 0.91, 0.91, and then it would be 2 times that value, which is 1.82. This shows me that the concentration of hydrogen decreases by 0.91. The concentration of iodine also decreases by that same amount, and the concentration of hydrogen iodide will increase by a value of 1.82. So here are the concentrations of all the reactants and products at equilibrium. 1.09 molar for hydrogen, 1.09 molar for iodine, 7.82 molar for hydrogen iodide. Let's go ahead and verify that this is in fact an equilibrium system by plugging in the equilibrium concentrations into the equilibrium constant expression. So 7.82 squared on the top, and the product of 1.09 times 1.09 on the bottom. And when you do this math on your calculator, hopefully you get a number that is pretty close to the number 51, indicating that we have an equilibrium system. So doing this math, I get 51.47, so that's close enough to 51 to establish that yes, this is an equilibrium system. Hopefully questions 3, 4, and 5 you found very similar, and again, you're working your way through processing the calculation involving a rice table. All right, this is question 6 in your packet. In question 6, we see a balanced chemical equation involving 1 mole of solid carbon reacting with 1 mole of carbon dioxide gas to produce 2 moles of carbon monoxide gas. It says solid carbon and carbon dioxide gas at 1160 Kelvin were placed in a rigid, previously evacuated 2.00 liter container, and a chemical reaction occurred producing carbon monoxide gas as represented by the equation shown above. As the reaction proceeded, the total pressure in the container was monitored. Solid carbon remained in the container at all times. Results are recorded in the table below. Now, as far as this particular initial set of conditions, we have reactants only and no products. We have solid carbon and carbon dioxide gas at time 0, but there's no carbon monoxide yet at time 0. So the reaction will proceed from left to right, from reactants to products, in order to achieve equilibrium. So as the reaction proceeds, 1 mole of gas, carbon dioxide, is converted into 2 moles of gas, carbon monoxide. So I would expect the pressure to increase over time as 1 mole of gas is converted into 2 moles of gas. Now we start off with an initial pressure of 5.00 atmospheres. That would just be the pressure of the carbon dioxide gas in the container at time 0. But as the reaction proceeds, the pressure increases. So at 2 hours, it's 6.26 atmospheres. The pressure continues to increase. At 4 hours, it's 7.09 atmospheres. The pressure continues to increase. At 6.0 hours, it's 7.75 atmospheres. It increases again to 8.37 atmospheres at 8 hours, but then from that point onward, the total pressure of gases in the container remains constant. So based on that last bit of information in the table, at what time during this experiment was equilibrium achieved, justify your answer. So based on the data in the table, I would say that equilibrium is achieved at time equals 8.0 hours, because from that point onward, the total pressure of gases in the container remains constant. Now, it is possible that the reaction did reach equilibrium at a time in between 6 hours and 8 hours, but we don't know exactly when that occurred. So based on the data in the table, from 8 hours onward, the total pressure of gases in the container remains constant. So that is how we can establish when equilibrium was achieved according to the data in this table. Okay, now let's move on to part B of this question. It says, calculate the number of moles of carbon dioxide gas initially placed in the container. Remember, at the beginning of the experiment, there was only solid carbon and carbon dioxide gas in the container. Assume that the volume of solid carbon in the container is negligible. So from the data at time 0, we know that the pressure of CO2 was equal to 5 atmospheres from the table. They told us that the volume of the container was 2.00 liters, and they also mentioned that the temperature was 1,160 Kelvin. So think back to something that I had mentioned earlier in Unit 3, how you can figure out the number of moles of gas if you know the pressure, the volume, and the temperature of that gas. Now, if you were thinking, can we use the ideal gas law to calculate the number of moles of carbon dioxide gas? The answer is yes, we absolutely can do that. What you are looking at here is a portion of the AP Chemistry Equations and Constant sheet. This is the section entitled Gases, Liquids, and Solutions. And not only do you see the ideal gas law, PV equals nRT, where P represents the pressure, V represents the volume, N represents the number of moles of gas, and T represents the Kelvin temperature, you can see the ideal gas law constant R, which is highlighted in the lower right corner of this slide, is 0.08206, and the units are liters, atmospheres per Kelvin per mole. Let's go ahead and set up the ideal gas law so we can calculate the number of moles of carbon dioxide gas initially placed in the container. So at the very beginning of this experiment, the initial pressure of carbon dioxide gas is 5.00 atmospheres. The volume of the container is 2.00 liters. The Kelvin temperature of this gas is 1,160 kelvins. And we're going to be solving for N the number of moles of gas. So if we rearrange the ideal gas law, solving for n, it would be n equals P times V divided by R times T. So let's plug in all of the information that we know. The pressure, 5.00 atmospheres. The volume, 2.00 liters. The ideal gas law constant, 0.08206, with units of liters, atmospheres per mole per Kelvin, and then the Kelvin temperature, 1160. So if we do this math to solve for the number of moles, 5 times 2 divided by 0.08206 divided by 1160, this is what I got on my calculator. I got 0.10505, and that would be the number of moles of carbon dioxide gas. Now, considering that the pressure, the volume, and the Kelvin temperature are all expressed with 3 significant figures, I'm going to round off my answer to 3 significant figures, and I get 0.105 for the number of moles of carbon dioxide gas. So again, that was an application of the ideal gas law in part B of this question. Now let's take a look at part C of this question. In part C, it says, for the reaction mixture at equilibrium at 1160 Kelvin, the partial pressure of carbon dioxide is equal to 1.63 atmospheres. Calculate the partial pressure of carbon monoxide in the container at equilibrium. Let's focus on the at equilibrium conditions from this table, and that would be when the total pressure of the gases is no longer changing over time. So the total pressure of the gas mixture at equilibrium is 8.37 atmospheres from the information in the table. And we were just given in part C that the partial pressure of carbon dioxide gas at equilibrium is 1.63 atmospheres. So how do we calculate the partial pressure of carbon monoxide in the container at equilibrium? Now, if you're thinking, does this relate to some other property of gases? Let's go back and take a look at that portion of the AP Chemistry equations and constant sheet, and you can see just a couple of equations below where it says ideal gas law, PV equals nRT. This equation for the total pressure of a gas mixture represents the sum of the individual partial pressures of the gas in the mixture. So the total pressure of a gas mixture is equal to the sum of the partial pressures of the individual gases. That's what we're going to go ahead and do in this problem. 8.37 atmospheres, the total pressure, minus the partial pressure of carbon dioxide, 1.63. That difference gives us a value of 6.74. So 6.74 atmospheres, that is the partial pressure of carbon monoxide in the container at equilibrium. Okay, now let's take a look at part D of this question. It says, write the expression for the equilibrium constant, Kp, for this reaction, and calculate the value of Kp at 1160 Kelvin. So in part C, we determined the partial pressure of each gas in the mixture at equilibrium. We know how to write the Kp expression. It's products over reactants, and then we can plug in the values for the pressure of the gases that we were able to figure out in part C. Remember that solids and pure liquids are not included in the reaction quotient or in the equilibrium constant expression, so solid carbon will not be featured in the Kp for this reaction. So it's products over reactants, partial pressure of carbon monoxide, squared, because there's a coefficient of 2 for that particular substance in the balanced equation, divided by the partial pressure of carbon dioxide. Again, from part C, the partial pressure of CO2 was given to us as 1.63 atmospheres, and then we calculated the partial pressure of carbon monoxide, 6.74 atmospheres. Let's go ahead and plug in those values into the Kp expression. So 6.74 squared divided by 1.63. Now, when you use a Kp, you do have to use pressure in atmospheres, So that unit is already present, but the final answer for K will not have any units. Equilibrium constants are dimensionless quantities. So 6.74 squared divided by 1.63, on my calculator I get 27.87. I will round this off to 3 significant figures, so I'll say 27.9. So that is the answer to part D. Now let's move on to part E. A second trial of this experiment is carried out at the same temperature, 1160 kelvins, with the same initial amount of carbon and carbon dioxide. So that's the same as the original trial, but here's the difference. A solid catalyst is placed in the reaction vessel. Do you predict that the total pressure of the gas mixture at equilibrium will be less than, greater than, or equal to the total pressure at equilibrium in trial 1 in the absence of a catalyst? Justify your prediction. Assume that the volume of the solid catalyst is negligible. So will a catalyst change the amount of either carbon monoxide or carbon dioxide that is present at equilibrium? Now, here I have a diagram for you. This is not from this particular packet, but it's from the previous packet, and I showed this in a previous video. I'm just using this as an example of you start with a particular amount of either reactant or product. In this case, we began with a total pressure of 8 atmospheres for the reactant, and then as the reaction proceeded, eventually equilibrium was reached. From 60 seconds in this graph, the pressures of the reactant and the product remain constant over time. I'm using this as an example to talk about a visual for what happens if a catalyst were added to a reaction. So equilibrium was reached in 60 seconds. How would the data from this experiment be affected if a catalyst were added to the reaction mixture? Well, a catalyst will speed up the reaction, but because this is a reversible reaction, it will not only speed up the rate of the forward reaction, it will also speed up the rate of the reverse reaction. So this catalyst is not going to affect the amounts, either concentrations or partial pressures of the reactants and the products at equilibrium. It will simply allow you to reach equilibrium more quickly. So to graph that, it would look something like this, where the concentration or the pressure of the reactants and the products, they would change more quickly, but once equilibrium was achieved, the value for either pressure or concentration would be the same. So here, perhaps the diagram I'm showing you would reach equilibrium for that catalyzed experiment, maybe not at 60 seconds, maybe around 35 seconds. But the most important point here is that when you add a catalyst, an equilibrium can be reached more quickly, but it's going to have the same values for either the concentrations or the pressures of the reactants and the products. So the answer to part E is the following. The total pressure of the gas mixture at equilibrium in trial 2 with the catalyst added will be equal to the total pressure at equilibrium in trial 1 in the absence of a catalyst. Although a catalyst would cause the system to reach equilibrium more quickly, it will not affect the value of the equilibrium constant, Kp, or the amounts of products and reactants present at equilibrium. Okay, now let's move on to part F of this question. In another experiment involving the same reaction, a rigid 2.00 liter container initially contained 10 grams of solid carbon and a mixture of both carbon monoxide and carbon dioxide. The initial values for the partial pressures of the gases were each equal to 3.00 atmospheres. The system is allowed to reach equilibrium at 1160 kelvins. Solid carbon remained in the container at all times. Now this is going to be a Q versus K situation. Do you predict that the partial pressure of carbon dioxide at equilibrium is less than or greater than 3 atmospheres? Justify your answer by comparing the value of the reaction quotient, Qp, with the value of the equilibrium constant, Kp, at 1160 kelvins. So earlier, we had already calculated the value of Kp for this particular reaction at this temperature. So we have to figure out the value of Q, and you don't necessarily have to make a rice table to answer this part of the question. All you're really doing is comparing Q versus K, but you will use a rice table in part G, so that's why I'm just showing it here on the slide just to kind of get started. Let's fill in the initial amount. In this case, partial pressure of carbon dioxide is 3.00 atmospheres, and the partial pressure of carbon monoxide is also 3.00 atmospheres. I don't need to worry about any amount for carbon because carbon is not featured in the equilibrium expression. So as long as there is solid carbon present in the container at all times, it is going to participate in the reaction, but we don't need to keep track of it as a concentration or pressure. So compare Q with Kp in order to determine if there will be a net conversion from left to right, from reactants to products, or if there will be a net conversion from right to left, from products to reactants. And remember that the Qp expression, it looks identical to the Kp expression. The only difference is that we're plugging in the concentrations, or in this case, the partial pressures, at any point during the reaction, whereas Kp, you plug in the values present at equilibrium. So here we have these initial conditions, 3 atmospheres for the pressure of carbon monoxide, 3 atmospheres for the pressure of carbon dioxide. Here's the Qp expression, pressure of carbon monoxide squared divided by the pressure of carbon dioxide. So 3 squared divided by 3 is equal to 9 over 3, or 3. Recall from earlier in this question, the Kp is 27.9. So since 3 is less than 27.9, now we know that the reaction quotient is less than the equilibrium constant. So if Qp is less than Kp, when Q is less than K, that means that either there are too many reactants or not enough products. So a net conversion from left to right, from reactants to products, will occur until equilibrium is achieved and Q equals K. So now that we know that the system will proceed from left to right, the concentration of carbon dioxide, a reactant, will go down. It's going to go down by X because we don't know what that is. And the partial pressure of carbon monoxide, a product, will increase, and it's going to go up by 2x because there is a coefficient of 2 in the balanced equation. So the answer to part F, do you predict that the partial pressure of carbon dioxide at equilibrium will be less than or greater than 3 atmospheres? The answer is less than. Since Q is less than K, this results in a net conversion of reactants to products. So the partial pressure of carbon dioxide at equilibrium will be less than 3 atmospheres. Now, I mentioned in part G, we're going to need a rice table, which is why I kind of set this up to prepare us for part G. Let's take a look. When the system described in part F has reached equilibrium at 1,160 kelvins, the total pressure of gases in the container is equal to 7.61 atmospheres. So that means that the sum of the partial pressure of carbon dioxide plus the partial pressure of carbon monoxide is equal to 7.61 atmospheres. Let's use our rice table to calculate the partial pressure of each gas in the container at equilibrium. So here's our rice table. We know that the system will proceed from left to right, from reactants to products. We know that carbon dioxide's pressure will go down, and it goes down by X because there's a coefficient of 1 for the carbon dioxide in the balanced equation. The carbon monoxide's pressure will increase, and it's going to be plus 2X because there is a coefficient of 2 for carbon monoxide in the balanced equation. Remember that the change row of your rice table, those amounts, the magnitude of those changes will always be in proportion to the coefficients from the balanced equation. So now at equilibrium, we have carbon dioxide. The pressure is 3 minus X. And at equilibrium, the pressure of the carbon monoxide will be 3 plus 2X. How do we use the total pressure of 7.61 atmospheres to solve for X? Well, if the total pressure is the sum of the individual partial pressures of each gas, all we have to do is add these two values together. So 3 minus x plus 3 plus 2x equals 7.61 atmospheres, which is the total pressure at equilibrium. Now we can just solve for x, pretty simple algebra. So 3 plus 3 is 6, negative x plus 2x is x. So we have 6 plus x equals 7.61 atmospheres. X equals 7.61 minus 6, or 1.61 atmospheres. And now that we know the actual number for the change, we can go back to our rice table and fill that in. So we know the pressure of the carbon dioxide decreases by 1.61 atmospheres, and the pressure of the carbon monoxide will increase by 2x, or 2 times 1.61. So that's going to increase by 3.22. Let's go ahead and do the math. 3 minus 1.61 is equal to 1.39 atmospheres, and 3 plus 3.22 is equal to 6.22 atmospheres. So it says calculate the partial pressure of carbon dioxide, which is 1.39 atmospheres, and carbon monoxide, which is 6.22 atmospheres. Now, just as a check, let's see if these numbers, the partial pressures of each gas at equilibrium, let's see if when we plug them in to the equilibrium constant expression, if we get a number that's sort of close to 27.9. So 6.22 squared divided by 1.39. When I do that math on my calculator, I get 27.8. That's pretty close to 27.9, so I'm satisfied that these values are, in fact, the equilibrium system for this particular reaction. All right, our next topic in the packet is topic 7.8, representations of equilibrium. Here is an essential knowledge statement from the AP Chemistry course and exam description. Particulate representations can be used to describe the relative numbers of reactant and product particles present prior to and at equilibrium, and the value of the equilibrium constant. This is question 7 from your packet. It says, substance X2 reacts with Y according to the equation above, in which 1 mole of X2 reacts with 2 moles of Y to produce 1 mole of X2Y2. A particulate representation of the reaction is also shown above, in which 1 particle of X2 reacts with 2 particles of Y to produce 1 particle of X2Y2. Part A, write the equilibrium constant expression, Kc, for the reaction represented by the equation above. So because it's Kc, we're going to use concentrations. We know it's products over reactants. So the Kc for this particular equation would be concentration of X2Y2 divided by the product of the concentration of X2 times the concentration of Y squared, because there is a 2 as a coefficient of Y in the balanced equation. Part B, the particulate diagram shown at right represents the reaction mixture after equilibrium has been achieved at 500 kelvins. Assume that each particle in the diagram represents 1 mole, and that the volume of the reaction vessel is 1.00 liters. Use the information from this diagram to calculate the value of the equilibrium constant Kc for this reaction at 500 kelvins. So the first thing I'm going to do is count the number of each type of particle in this diagram. Then I will plug in those values into the Kc expression. Since each particle represents 1 mole and the volume of the container is 1 liter, that means that each particle represents 1 mole per liter. So for the X2 particles, we have 1, 2, 3, 4, 5, 6, 7, 8 particles of X2. And then I can see that the number of particles of Y, there are 2 particles of Y in the diagram, and there are 2 particles of X2Y2 in the diagram. So those numbers are going to be plugged into the equilibrium constant expression, and those numbers represent the number of moles per liter based on the information for this diagram. So on the top, we have concentration of X2Y2, which would be 2 moles per liter. And on the bottom, we have the concentration of X2, which would be 8 moles per liter, times the concentration of Y, which is 2 moles per liter. And then don't forget, we have to square the concentration of Y because of the coefficient of 2 in the balanced equation. So the math that we're doing to calculate the value of Kc based on the information in this particle diagram would be 2 divided by the product of 8 times 2 squared. So when we do that math, we get 0.0625. So now that we know the value of the equilibrium constant, Kc, based on this information in the particle diagram, we can now move on to part C. In part C, we have 3 different particulate representations of the reaction mixture at various points in time. So what we have to do in part C is first count the particles so we can calculate the value of the reaction quotient for that moment in time for each diagram. Then, based on the value of the reaction quotient, QC, compare the value of QC with Kc and determine if the reaction mixture represented in the diagram is at equilibrium. And if the system is not at equilibrium, determine the direction, either toward the right, the products, or toward the left, the reactants. In which direction should the reaction proceed in order to reach equilibrium? So let's start with the first diagram. We'll count the particles. So the number of particles of X2Y2 are 1, 2, 3, 4, 5. So there's 5 X2Y2 particles, so 5 will go on top. And then the number of X2 particles, I see 3, so 3 goes on the bottom. And the number of Y particles, I see 2, that's going to be also on the bottom, and that number is going to be squared. So 5 divided by the product of 3 times 2 squared. Now we're going to find out if Q is greater than or less than K, which is 0.0625. When we do this math, we get 0.417. So clearly 0.417 is larger than K. And when Q is greater than K, there are either too many products or not enough reactants. And so a net conversion of right to left or from products to reactants will occur until equilibrium is achieved and Q equals K. So this system for this particle diagram is not at equilibrium. We just discovered that Q is greater than K. This would result in a net conversion of products to reactants or toward the left. Here's our next particle diagram. Let's count the particles. So I see 3 particles of X2Y2. I see 5 particles of X2. And I see 6 particles of Y. So it's going to be 3 divided by the product of 5 times 6 squared, based on the number of particles in the diagram. When we do this math, we get a reaction quotient, QC, of 0.0167. So comparing that to the value of Kc, we see that Q is less than Kc for this diagram. And if Q is less than K, then there are either too many reactants or not enough products. A net conversion of left to right, reactants to products, would occur until equilibrium is achieved and Q equals K. So for this system, there is a net conversion of reactants to products toward the right. And now for this third diagram, if we count the particles, I see 4 particles of X2Y2, I see 4 particles of X2, and I see 4 particles of Y. So it's going to be the reaction quotient 4 divided by the product of 4 times 4 squared. When we do this math, we actually get a value of 0.0625, which means Q is equal to K. For this diagram, the system is already at equilibrium. All right, moving on to our next topic. We actually have 2 topics that are going to be combined because they are so similar. So topic 7.9, Introduction to Le Châtelier's Principle, and topic 7.10, Reaction Quotient and Le Châtelier's Principle. Here are the essential knowledge statements from the AP Chemistry course and exam description for these two topics. Le Chatelier's principle can be used to predict the response of a system to stresses, such as addition or removal of a chemical species, change in temperature, change in volume, pressure of a gas phase system, or dilution of a reaction system. Le Chatelier's principle can be used to predict the effect that a stress will have on experimentally measurable properties such as pH, temperature, and color of a solution. A disturbance to a system at equilibrium causes Q to differ from K, thereby taking the system out of equilibrium. The system responds by bringing Q back into agreement with K, thereby establishing a new equilibrium state. Some stresses, such as changes in concentration, cause a change in Q only. A change in temperature causes a change in K. In either case, the concentrations or partial pressures of species redistribute to bring Q and K back into equality. All right, this is question 8 in your packet, and I will tell you this right now, although you'll figure it out as we go along. Questions 8, 9, and 10 all involve this same equilibrium system involving sulfur trioxide, SO3, sulfur dioxide, SO2, and molecular oxygen, O2. So here's question 8. It says sulfur trioxide gas, which is SO3, decomposes at high temperature to produce sulfur dioxide gas, SO2, and oxygen gas, O2, according to the equation above. A sample of SO3 was added to a previously evacuated rigid reaction vessel. The reaction represented by the equation above was allowed to proceed until it reached equilibrium at 1000 kelvins. The partial pressures were determined to be the following. Pressure of SO3 is equal to 3.43 atmospheres. Pressure of SO2 is equal to 2.00 atmospheres. And pressure of O2 is equal to 1.00 atmospheres. Part A, write the equilibrium constant expression, Kp, for the reaction, and calculate the value of Kp at 1000 kelvins. So we have products over reactants. Because it's Kp, we're going to use pressure and not concentration. So it's going to be the pressure of the SO2 squared times the pressure of the O2 divided by the pressure of the SO3 squared. Now we plug in the numbers, which are the partial pressures at equilibrium. So it's going to be 2 squared times 1 on the top, and it's going to be 3.43 squared on the bottom. When we do this math, we get the value of Kp at 1000 Kelvin based on the information in this question, and that works out to be 0.340. So now that we know the value of Kp, if there are any stresses or disturbances to the system that cause Q to become different than 0.340, then the system is going to respond and try to reestablish equilibrium and eventually return Q equal to this value. So 0.340 is the value of K. Let's take a look at various changes and stresses and disturbances, and we'll see this in questions 8, 9, and 10 in this packet. All right, so here's part B. Here is our first stress or disturbance to the system that already was at equilibrium. So part B says additional SO3 is added to the reaction vessel at 1000 kelvins until the partial pressure of SO3 is 6 atmospheres. Calculate the value of Qp at the moment that additional SO3 is added. So the number that we have for SO3 is now changed. It's not 3.43 atmospheres anymore. It's now 6 atmospheres. Again, Le Chatelier's principle focuses on what happens to the system in response to a stress such as addition or removal of a chemical species. And so a chemical species was just added to the system to cause a stress or a disturbance. So as you can see on this slide, the new pressure of SO3 is now 6 atmospheres. Let's plug in that number into the expression for the reaction quotient. So it's still going to be 2 squared times 1 on the top because those numbers didn't change, but on the bottom it's going to be 6 squared. Hopefully you can tell, even without using a calculator, that because we've increased the value of the number that's in the denominator of this expression, it's going to cause the value of Q to become less than K. Let's take a look. So we now have a new number, which is not 0.340. The system has been disturbed, so now it's 0.111. So Q becomes less than K. So there are too many reactants or not enough products. But in this case, we know there are too many reactants because we added SO3, so that is a reactant. So there's definitely too many reactants, and so a net conversion from left to right, from reactants to products, will occur until eventually equilibrium is reestablished and Q equals K. So again, Q is less than K. There is a net conversion of reactants to products toward the right, and so in part C, it says the addition of SO3 to the reaction vessel caused a disturbance in the equilibrium system that had already been established. So as the system reestablishes equilibrium at 1000 kelvins, which of the following statements should be true? Well, if we're going to proceed from left to right, that's going to cause additional SO2 to be formed. So the partial pressure of SO2 should increase until eventually equilibrium is reestablished and Q equals K. All right, so let's take a look at part D. When the equilibrium is reestablished at 1000 kelvins, the partial pressure of O2 in the reaction vessel is 1.34 atmospheres. Calculate the partial pressures of SO3 and SO2 when equilibrium is reestablished. So, as you are processing the information in part D, you're thinking, we know the partial pressure of O2 in the reaction vessel when equilibrium is reestablished. It's 1.34 atmospheres. But how are we going to figure out the partial pressures of SO3 and SO2 in the reaction vessel when equilibrium is reestablished? If you're thinking, would it be a good idea to make a rice table to solve this problem? The answer is yes. That's exactly what we're going to do. We're going to make a rice table. And for the reaction row of the rice table, you can see there's the balanced chemical equation with the appropriate coefficients. For the initial row of the rice table, let's go ahead and fill in the partial pressures at the moment that that stress or that disturbance occurred. So the partial pressure of SO3 is 6 atmospheres. The partial pressure of SO2 is 2 atmospheres. And the partial pressure of O2 is 1 atmospheres. We know that because Q is less than K, there's going to be a net conversion from reactants to products. So from left to right, that's going to cause the partial pressure of SO3 to decrease. It's going to cause the partial pressure of the products, SO2 and O2, to increase. And notice that what I did is I wrote the change in terms of X. So look at the change row of the table and look at the coefficients in the balanced equation. So because the coefficients from left to right are 2, 2, and 1, the magnitude of the change is 2x, 2x, and x from left to right. So SO3 is going to decrease. So at equilibrium, whenever it's reestablished, it's going to be 6 minus 2x. SO2 is going to increase. So at equilibrium, when that's reestablished, it's going to be 2 plus 2x. And then O2 will also increase. It's going to be 1 plus x. Now, this is not going to be complicated math. We're not going to have to use some fancy quadratic equation. They were nice enough to tell us in part D that when equilibrium is reestablished, the partial pressure of O2 in the reaction vessel is 1.34 atmospheres. So we can put that number in the final row of the rice table. So 1.34 now goes in that spot at equilibrium. And that's great, because now we can calculate x. The difference between 1 and 1.34 is 0.34, which means that now we can fill in the change row of the rice table with actual numbers instead of x values. So it's going to be 0.34 or 0.68 for the 2x. So the pressure of the SO3 is going to decrease by 0.68 atmospheres. The pressure of the SO2 is going to increase by 0.68 atmospheres. And then we already know that the pressure of the O2 has increased by 0.34 atmospheres. Let's go ahead and do the math from top to bottom. 6 minus 0.68 is 5.32 atmospheres. And obviously 2 plus 0.68 is 2.68 atmospheres. So it said calculate the partial pressures of SO3 and SO2 when equilibrium is reestablished. Hopefully you can see that that's why a rice table makes it very easy. It's a good strategy for solving this kind of problem. Now, I mentioned that equilibrium is reestablished. Let's go ahead and check to see if now Q equals K for this system. So to plug in the numbers in the final row of the rice table, let's see if we can get a value of approximately 0.34 for this system. So on the top, it's going to be pressure of SO2 squared times pressure of O2. That's going to be 2.68 squared times 1.34. And on the bottom, it's going to be pressure of SO3 squared. So it's going to be 5.32 squared. If you do this math on your calculator, hopefully you will get a number that is equal to 0.34. And yes, we do. So let's take a look graphically at what happened before the stress occurred, and then what happened as the system reestablished equilibrium. So equilibrium has been reestablished after it was disturbed. What was the disturbance? Additional SO3 was added. Let's take a look at this graph here. So on the left, you can see that equilibrium had already been established, and those numbers were the pressures of each gas when equilibrium had already been achieved. Then you see a big spike in the partial pressure of SO3. So the stress was that additional SO3 was added to the reaction vessel. And at that moment, it caused Q to become less than K. So how did the system respond? Well, some of the SO3 was consumed, so that pressure decreased, and then additional SO2 and O2 was produced, so those pressures increased. But then, as the system shifted from left to right, there was a net conversion of reactants to products. These new numbers are now the new pressures for each gas, and equilibrium has been re-established. So Le Chatelier's principle is stated as follows. If a system at equilibrium is disturbed by a stress, the reaction will proceed in a certain way so as to counteract the effect of the disturbance. Stresses that can occur to disturb an equilibrium system include the following: the addition or removal of certain substances, a change in the volume of the reaction vessel for a gaseous system, the addition or removal of water for an aqueous system, or a change in temperature. And the change in temperature is special because if the temperature remains constant, the value of the equilibrium constant K also remains constant. So temperature changes are the only thing that will actually change the value of the equilibrium constant K, which we will see later on in this video. So addition or removal of certain substances, as we've seen so far. Question 9 and question 10 involve this same system involving SO3, SO2, and O2. Let's take a look at question 9. Question 9 says a reaction vessel contains a mixture of SO3, SO2, and O2 at 1000 kelvins with the following values of partial pressure. Pressure of SO3 is 9.70 atmospheres. Pressure of SO2 is 4.00 atmospheres. And pressure of O2 is 2.00 atmospheres. Part A, is this system at equilibrium? Justify your answer with a calculation. So to check, we're going to do products over reactants. It's going to be pressure of SO2 squared times pressure of O2 divided by pressure of SO3 squared. So that's our QP expression, and we'll plug in the number 4 for the pressure of SO2. It's going to be 4 squared. We're going to plug in 2 for the pressure of O2, so 4 squared times 2 on the top, And on the bottom, it's going to be 9.70 squared. If we do this math on our calculator, we get 0.340. So yes, the system is at equilibrium because Q equals K. Now in question 8, the disturbance was additional SO3, which is a reactant, was added. Let's take a look at the stress in part B of question 9. So additional SO2, which is actually a product, is added to the reaction vessel at 1000 Kelvin until the partial pressure of SO2 is now 8 atmospheres. So calculate the value of QP at the moment that additional SO2, which is a product, is added. So in question 8, they added extra SO3, which is a reactant. Here in question 9, they're adding more SO2, which is a product. Hopefully you can tell, even without a calculator, that the number that we are changing is in the numerator of the expression. So instead of 4 squared times 2 divided by 9.70 squared, it's now 8 squared times 2 divided by 9.70 squared. And if you increase the value of the number in the numerator, it's going to cause Q to become larger than K. So if you do this math on your calculator, 8 squared times 2 divided by 9.70 squared, yes, we get a number 1.36, which is larger than K, which is 0.34. So Q is greater than K, and you know that when Q is greater than K, there are too many products or not enough reactants. But in this case, there's definitely too many products because additional SO2 was added to disturb the equilibrium. So a net conversion from right to left, from products to reactants, will occur until equilibrium is achieved or reestablished and Q equals K. So the addition of SO2 to the reaction vessel, again, SO2 is a product, caused a disturbance in the equilibrium system that had already been established. As the system reestablishes equilibrium at 1000 kelvins, which of the following statements should be true? So we're talking about how the partial pressure of O2 will change as the system reestablishes equilibrium. Well, remember, Q is greater than K. There should be a net conversion from products to reactants. And since O2 is a product, some of the O2 is going to be consumed as the system reestablishes equilibrium, causing the partial pressure of O2 to decrease until eventually equilibrium is reestablished and Q equals K. So right now, the pressure at the moment the stress occurred, the pressure of O2 is 2 atmospheres. Take a look at part D. It says when equilibrium is reestablished at 1000 kelvins, the partial pressure of O2 in the reaction vessel is 1.13 atmospheres. See, it did decrease. Calculate the partial pressures of the SO3 and the SO2 when equilibrium is reestablished. Now, you recall in question 8, we made a rice table. We're going to do the same thing. We're going to make a rice table, and we're going to fill in the initial row of the rice table, the partial pressure of each gas at the moment that the stress occurred. So SO3, which is the reactant, is still 9.70 atmospheres. That wasn't changed. The SO2 was increased to a value of 8 atmospheres. So that was the stress, that was the disturbance, that was the change. And O2 is 2 atmospheres. But here comes the shift from right to left. There's a net conversion from products to reactants. That's going to cause SO3 to increase, and it's going to cause SO2 and O2 to decrease. Again, pay close attention to that change. I'm writing the change in terms of x, and I'm saying plus 2x, minus 2x, and minus x. Again, that's consistent with the coefficients in the balanced equation. So at equilibrium, when it's been reestablished, the pressure of SO3 will be 9.70 plus 2x. The pressure of SO2 will be 8 minus 2x. And the pressure of O2 will be 2 minus x. They told us that the partial pressure of O2 when equilibrium is reestablished is 1.13 atmospheres. So we can place that number in the final row of the rice table, just like we did in question 8. So 1.13 atmospheres goes right here. And now that we know the difference between 2 and 1.13 is 0.87, we've just calculated the value of x, we can fill in all of the amounts in the change row of the rice table with actual numbers and not expressions in terms of x. So 0.87 times 2 is 1.74. So the pressure of SO3 increases by 1.74 atmospheres. The pressure of the SO2 decreases by 1.74 atmospheres, and we know the pressure of O2 decreased by 0.87 atmospheres. Let's do the math from top to bottom. 9.70 plus 1.74 becomes 11.44 atmospheres, and 8 minus 1.74 is 6.26 atmospheres. So calculate the partial pressures of SO3 and SO2 when equilibrium is reestablished. So we've done that. We filled in all of the numbers in the final row of the rice table. Let's go ahead and check and verify, do these three new numbers that we have now represent an equilibrium system? So let's go ahead and plug in those three values into the equilibrium constant expression, and hopefully we get 0.34 again. So on the top, it's going to be pressure of SO2 squared times pressure of O2. So 6.26 squared times 1.13. And on the bottom, it's going to be pressure of SO3 squared. That's going to be 11.44 squared. So when you do this math on your calculator, you hope that you get 0.34, and we get 0.338. Close enough, looks good. So equilibrium has been reestablished after it was disturbed, this time by the addition of SO2 to the reaction vessel. Let's take a look graphically at what happened. So we had an equilibrium with these three numbers that were establishing equilibrium before the stress, before the disturbance. Now, what was the stress? Additional SO2 was added. So you can see that spike in the partial pressure of SO2. So at that moment, Q became greater than K. And so as the equilibrium responded by shifting toward the reactants, as there was a net conversion from products to reactants, that caused some of the SO2 to be consumed. So you can see that that partial pressure decreased. It also caused some of the O2 to be consumed, so that pressure decreased, and it caused the additional formation of SO3, which is why that partial pressure increased. And those new numbers on the far right side of the diagram, those are the new pressures when equilibrium has been reestablished. Before we take a look at question 10, we've already seen two examples of the addition of a substance. So question 10 is going to involve the removal of a substance. Let's take a look. So here's question 10. It says a reaction vessel contains a mixture of SO3, SO2, and O2 at 1,000 kelvins with the following values of partial pressure. The pressure of SO3 is 10.29 atmospheres. The pressure of SO2 is 3.00 atmospheres, and the pressure of O2 is 4.00 atmospheres. Part A, is this system at equilibrium? Justify your answer with a calculation. So it's going to be products over reactants. It's going to be pressure of SO2 squared times pressure of O2 divided by the pressure of SO3 squared. So the math you're going to plug into your calculator would be 3 squared times 4 divided by 10.29 squared. And when you do that math, you get 0.340. So yes, the system is at equilibrium because Q equals K. Now in question 8, the stress was adding more SO3, which was a reactant. In question 9, it was adding more SO2, which is a product. Let's see in question 10 what the stress is going to be. Some of the SO2 is removed from the reaction vessel at 1,000 kelvins, reducing the partial pressure of SO2. So it was 3 atmospheres, now it's down to 1 atmosphere. So they've reduced it. So they didn't add a chemical, they took a chemical away, and they took away some of the product. So think about how that would affect the value of Q. You can kind of think of this before you do the math. They're taking away some of the SO2. So because it's products over reactants, one of the numbers in the numerator of this expression has been decreased to a smaller value. So that should cause Q to become less than K. Let's take a look. It's going to be 1 squared instead of 3 squared. So 1 squared times 4 divided by 10.29 squared, and we get 0.038, which, yes, this is smaller than K. When Q is less than K, there are too many reactants or not enough products. In this case, it's not enough products. They took away some of the SO2, which is a product, so that caused Q to become less than K, and there should be a net conversion from left to right, from reactants to products, until eventually equilibrium will be reestablished again. So Q is less than K. There is a net conversion of reactants to products from left to right. Let's see how this will affect the partial pressure of O2. So the removal of SO2 from the reaction vessel caused a disturbance in the equilibrium system that had already been established. As the system reestablishes equilibrium at 1,000 kelvins, which of the following statements should be true? If we are proceeding from left to right, from reactants to products, and since O2 happens to be a product, the partial pressure of O2 should increase until eventually Q equals K. So right now, the partial pressure of O2 is 4 atmospheres. Let's take a look at part D. It says when equilibrium is reestablished at 1,000 kelvins, the partial pressure of O2 in the reaction vessel is 4.70 atmospheres. So yes, it did increase. Calculate the partial pressures of SO3 and SO2 when equilibrium is reestablished. Are we going to make a Rice table? Yes. Just like in question 8 and 9. Here's our Rice table. And at the moment that the stress occurred, we have a pressure of SO3, which is 10.29 atmospheres. That was not changed. We have a partial pressure of SO2 of 1 atmosphere. So that was the one that was decreased from a higher value to a lower value. And then at the moment the stress occurred, the partial pressure of O2 is 4 atmospheres. Because there is a net conversion from reactants to products from left to right, that's going to cause the SO3 pressure to go down and cause the pressure of SO2 and O2 to go up. So you can see the magnitude of the change is 2x, 2x, and x, consistent with the coefficients of 2, 2, and 1. So at equilibrium, when it's been reestablished, the pressure of SO3 should be 10.29 minus 2x. When equilibrium is reestablished, the pressure of SO2 should be 1 plus 2x. And when equilibrium is reestablished, the pressure of O2 should be 4 plus x. But we already know from what they told us in part D that at equilibrium, when this equilibrium has been reestablished, the pressure of O2 is 4.70 atmospheres. Let's place that number in the final row of the Rice table, so it goes right here. And of course, 4 plus 0.7 is 4.7. So if x is 0.7, that means that 2x would be 1.4. So the SO3 has decreased. The pressure has decreased by 1.4. The pressure of the SO2 has increased by 1.4. And of course, the pressure of the O2 increases by 0.7. Let's do the math from top to bottom. 10.29 minus 1.4 is 8.89 atmospheres. And then 1 plus 1.4 is 2.40 atmospheres. It said in part D, calculate the partial pressures of SO3 and SO2 when equilibrium is reestablished. We made the Rice table, we solved for x, we calculated the partial pressure of all 3 substances in the reaction vessel when equilibrium has been reestablished. Let's go ahead and do that final check to see if these 3 new numbers in fact represent an equilibrium system. So it's going to be products over reactants, the partial pressure of SO2 squared times the partial pressure of O2 divided by the partial pressure of SO3 squared. So 2.40 squared times 4.70 divided by 8.89 squared. So when you do that math on your calculator, you hope that you get a number that's pretty close to 0.34, and in fact, we do. 0.343, that's pretty close. So we're satisfied that yes, equilibrium has been reestablished after it was disturbed, this time by the removal of SO2. Let's take a look graphically at what happened. So we had an equilibrium system with these three numbers before the stress occurred. Now you can see instead of a spike going upward, you can see it falling downward. So the SO2, which was removed, caused that rapid decrease in the pressure of SO2. So now the system has to respond to this stress. And if Q is less than K, there's going to be a net conversion from left to right. And as it will shift toward the products from left to right, it causes the SO3 pressure to go down a little bit, which you can see there on the diagram. And it caused the pressure of the O2 and the SO2 to increase a little bit. So you can see on the right side of this graph, these are the new values for the partial pressure of SO3, O2, and SO2 when equilibrium has been reestablished for this system. Now, you've seen in questions 8, 9, and 10 the addition or removal of a substance. Now, in questions 11, 12, and 13 in the packet, we're going to look at what happens if a volume change occurs. There's going to be a change in the volume of the reaction vessel for a gaseous system. So here in question 11, we have a new equilibrium system to consider in which 1 mole of N2O4 gas decomposes to produce 2 moles of NO2 gas. We are already given that the Kp value is 0.21 at a temperature of 373 kelvins. It says a reaction vessel with a volume of 2.00 liters contains a mixture of N2O4 and NO2 at 373 Kelvin with the following values of partial pressure. The pressure of N2O4 is 4.77 atmospheres, and the pressure of NO2 is 1.00 atmospheres. Part A, is this system at equilibrium? Justify your answer with a calculation. So it's going to be products over reactants, the pressure of the NO2 squared divided by the pressure of the N2O4. So the math you're doing on your calculator would be 1 squared divided by 4.77. And when you do that math, you get 0.210. So yes, the system is at equilibrium because right now Q equals K. But here comes the stress. We're not adding a chemical. We're not removing a chemical. We are changing the volume of the reaction vessel. So in part B, the volume of the reaction vessel is decreased from 2 liters to 1 liter, while the temperature is held constant at 373 kelvins. At the moment the volume is decreased from 2 liters to 1 liter, what is the partial pressure of each gas? So just to remind you about the variables for pressure and volume, we learned about gas properties back in Unit 3. So if you decrease the volume of a reaction vessel by half, then the partial pressures are going to be increased by a factor of 2. So the volume of the vessel is decreased to half its original volume. So the partial pressure of each gas is doubled. So 4.77 times 2 is 9.54, and obviously 1 times 2 is 2. So the new pressures as a result of this stress or this disturbance are 9.54 atmospheres for the pressure of N2O4 and 2 atmospheres for the pressure of NO2. Let's go ahead and calculate the value of QP for this system at the moment that the stress or the disturbance occurs. So it's going to be pressure of NO2 squared divided by pressure of N2O4. So the math you're doing is 2 squared divided by 9.54. And 2 squared divided by 9.54 is equal to 0.419. So compare 0.419 with the Kp, which is 0.21. So you can see that Q at this moment is larger than K. And when Q is greater than K, there will be a net conversion of products to reactants from right to left until eventually equilibrium is reestablished and Q equals K. So because there's going to be a net conversion from right to left, from products to reactants, what's going to happen to the partial pressure of NO2? Let's take a look at part D. It said the change in the volume of the reaction vessel caused a disturbance in the equilibrium system that had already been established. As the system re-establishes equilibrium at 373 Kelvin, which of the following statements should be true? So because there is a net conversion from products to reactants, from right to left, and since NO2 happens to be a product, the partial pressure of NO2 will decrease until eventually Q equals K again. So part E, when equilibrium is reestablished at 373 kelvins, the partial pressure of N2O4 in the reaction vessel is 9.82 atmospheres. Calculate the partial pressure of NO2 when equilibrium is reestablished. So we know that before the stress, equilibrium had been established. Then the stress was to decrease the reaction vessel from 2 liters to 1 liter. That caused the partial pressure of each gas to increase. So at that moment, the partial pressure of N2O4 was 9.54 atmospheres, and the partial pressure of NO2 was 2.00 atmospheres. Because there is a net conversion from products to reactants, from right to left, the partial pressure of the N2O4 will increase, so we'll say plus X, and the partial pressure of the NO2 will decrease, and we'll say minus 2X. Again, notice that it's X and 2X because the coefficients from left to right are 1 and 2. So the magnitude of change is always proportional to the coefficients in the balanced equation. So 9.54 plus X is the pressure of the N2O4 when equilibrium is reestablished, and 2 minus 2X is the pressure of the NO2 when equilibrium is reestablished. Now that number that they gave us in part E is 9.82. That's the pressure of the N2O4 in the reaction vessel when equilibrium is reestablished. So 9.82 goes in the final row of the Rice table right here, 9.82. That's a difference of, so 9.54 plus 0.28 equals 9.82. And since X is 0.28, that means that 2X would be twice that value, so 0.56. The pressure of the NO2 has decreased from 2 minus 0.56 becomes 1.44. So we now know the partial pressure of the NO2 when equilibrium is reestablished. Again, we're using our Rice table to keep track of everything. So 9.82 is the partial pressure of N2O4, and 1.44 is the partial pressure of the NO2. Of course, we're going to check it. So we're going to plug those numbers into the equilibrium constant expression, pressure of NO2 squared divided by pressure of N2O4. So 1.44 squared divided by 9.82. We're hoping we get a number that's pretty close to 0.21 to show that equilibrium is reestablished. And yes, that number looks good. So equilibrium has been reestablished after it was disturbed, not by adding a chemical, not by removing a chemical, but by decreasing the volume of the vessel. Now, you might be thinking, in terms of the shift in equilibrium, the fact that it proceeded from right to left, would that always happen? Every time you decrease the volume of a reaction vessel for a gaseous equilibrium, is it always going to shift from the products to the reactants? And the answer is no. It depends on the relative number of moles of gas. So the fact that we have 1 mole of gas on the left in this reaction and 2 moles of gas on the right What the system did was to shift to whichever side of the equation had a smaller number of moles of gaseous particles. Let's take a look at what happened. So before the stress occurred, we have these values for the pressure of N2O4 and NO2. Now, the moment that the stress occurred, each of those pressures was doubled. So the volume of the vessel decreased by half, so the new pressures have been doubled. Then the system is going to shift to whichever side of the equation has a lower number of moles of gaseous particles. That's how it responds to this sudden increase in pressure. So it's going to shift to the side of the equation that has a fewer number of moles of gaseous particles, because that will reduce the number of collisions with the container walls and slightly decrease the pressure. Take a look. Here are the new numbers when equilibrium is reestablished. Now watch what happens if you add the two pressures together. At the moment the stress occurred, it was 9.54 plus 2. So 11.54 was the total pressure. And now look at the new system. The total pressure is 9.82 plus 1.44, which is 11.26. So focus on those numbers that are on the slide there in blue. It was 11.54 at the moment the stress occurred, and now it's 11.26. So the total pressure was in fact decreased slightly. So that's how the system responded to this decrease in the volume of the vessel. The partial pressures of all the gaseous species were increased at that moment, and because the system shifted toward the side of the equation that had a lower number of moles of gaseous particles, that was a way for the system to relieve the stress and establish a new equilibrium. All right, so that was question 11. We're now going to take a look at question 12, and we've already seen what happens when the volume of the reaction vessel decreases. In question 12, we're going to see what happens when the stress is to increase the volume of the reaction vessel. So here in question 12, there are a lot of similarities. We have the same equilibrium system involving 1 mole of N2O4 decomposing to produce 2 moles of NO2. The value of Kp is the same at 0.21 at 373 Kelvin. It says a reaction vessel with a volume of 1.00 liters contains a mixture of N2O4 and NO2 at 373 kelvins with the following values of partial pressure. Pressure of N2O4 is 19.02 atmospheres. Pressure of NO2 is 2.00 atmospheres. Part A is the system at equilibrium. Justify your answer with a calculation. So it's pressure of NO2 squared divided by pressure of N2O4. So when you pick up your calculator, it's going to be 2 squared divided by 19.02. And when you do that math, you get 0.21. So yes, the system is currently at equilibrium because Q equals K. Now, the stress in question 12 is different than the stress in question 11. We've already seen what happens when you decrease the volume of the reaction vessel. So take a look. Now, the volume of the reaction vessel is increased from 1 liter to 2 liter, while the temperature is held constant at 373 Kelvin. At the moment the volume is increased from 1 liter to 2 liters, what is the partial pressure of each gas? So instead of doubling them like we did before, now we're going to cut them in half. So when the volume of the vessel is doubled, the partial pressure of each gas is decreased by half. So 19.02 divided by 2 is 9.51, and obviously 2 divided by 2 is 1. So these are the new pressures at the moment that the stress occurred. Based on your answer to part B, which are these pressures of 9.51 and 1.00 atmospheres, what is the value of QP for this system? So pressure of NO2 squared divided by pressure of N2O4. It's going to be 1 squared divided by 9.51, and we get a value of Q of 0.105. Compare that to Kp, which is 0.21, so 0.105 is less. When Q is less than K, there will be a net conversion from left to right, from reactants to products. And so the change in the volume of the reaction vessel just now from 1 liter to 2 liters caused a disturbance in the equilibrium system that had already been established. As the system reestablishes equilibrium, which of the following statements should be true? Well, if we're going to have a net conversion from left to right, from reactants to products, and since NO2 happens to be a product, that means the partial pressure of NO2 will increase until eventually equilibrium is reestablished and Q equals K. So when equilibrium is reestablished, the partial pressure of N2O4, it was 9.51. It's going to drop down to 9.31. Let's make our Rice table, and we'll calculate the partial pressure of NO2 using our Rice table. So initially, at the moment that the stress occurred, the partial pressure of N2O4 is 9.51 atmospheres, and the partial pressure of NO2 is 1.00 atmospheres. There is a net conversion from left to right, from reactants to products, that causes the value of the pressure of N2O4 to decrease. So we'll say minus X. It will cause the pressure of NO2 to increase. And we'll say plus 2X. Again, there's that 1:2 ratio based on the coefficients. And they're telling us that the partial pressure of N2O4 is 9.31. So 9.51 minus X, 1 plus 2X. Let's put some actual numbers in that final row of the Rice table. So 9.31 will be the pressure of N2O4, and that goes in the bottom of the Rice table right here. The difference between 9.51 and 9.31, that's a difference of 0.20. So if X is equal to 0.20, that means that 2X would be twice that amount, or 0.40. So the pressure of N2O4 decreases by 0.20 atmospheres, and the pressure of NO2 increases by 0.40 atmospheres. So the final pressure of NO2 when equilibrium has been reestablished is 1.40 atmospheres. Now that we know the partial pressure of each gas when equilibrium is reestablished, let's go ahead and check it and make sure that that works. In our equilibrium constant expression, it's going to be the pressure of NO2 squared divided by the pressure of N2O4. So 1.40 squared divided by 9.31. When you do this math on your calculator, you hope you get a number that's pretty close to 0.21, and in fact, we do. So we have now confirmed that yes, equilibrium has been reestablished, but this time the disturbance was increasing the volume of the vessel. So back in the previous question, there was a sudden increase in the pressure of both gases. Here, we have a sudden decrease in the pressure of both gases. So the volume of the vessel increased. The partial pressures were suddenly dropped to half their original values. And so how did the system respond? Well, it's going to respond by trying to increase the pressure. That's going to be the response to the disturbance. There was a sudden decrease in pressure for both gases. So it's going to shift to whichever side of the equation has a higher number of moles of gaseous particles. And that happened to be from left to right. Take a look. At the moment the stress occurred, the total pressure was 9.51 plus 1, or 10.51 atmospheres. So watch what happens when equilibrium is reestablished. 9.31 plus 1.40 is 10.71. So can you see, focusing on how the system responded, the total pressure went from 10.51 to 10.71. So in fact, it did, by shifting toward the side of the equation that has a higher number of moles of gaseous particles, it was able to respond to that stress by slightly increasing the pressure inside the reaction vessel. Okay, now let's move on to question 13. We have one more example of changing the volume of the reaction vessel for a gaseous equilibrium system, but something interesting is going to happen with this particular system. In this system, we have 1 mole of hydrogen reacting with 1 mole of iodine to produce 2 moles of hydrogen iodide. We are given that the Kp is equal to 51 at 448 degrees Celsius. So question 13 says, a reaction vessel with a volume of 2.00 liters contains a mixture of hydrogen, iodine, and hydrogen iodide at 448 degrees Celsius with the following values of partial pressure. The pressure of the hydrogen is 1.20 atmospheres, pressure of the iodine is 1.20 atmospheres, and the pressure of the hydrogen iodide is 8.57 atmospheres. Part A. Is this system at equilibrium? Justify your answer with a calculation. So for this system, it's going to be products over reactants, the pressure of the hydrogen iodide squared, because there's a coefficient of 2 for that chemical, divided by the product of the pressure of hydrogen times the pressure of iodine. So 8.57 squared divided by the product of 1.20 times 1.20. When you do that math on your calculator, you get that Qp equals 51. So this system is at equilibrium because right now Q equals K. So here comes the stress. In part B, it says the volume of the reaction vessel is decreased from 2 liters to 1 liter while the temperature is held constant at 448 degrees Celsius. At the moment that the volume is decreased from 2 liters to 1 liter, what is the partial pressure of each gas? So remember that when you decrease the volume of the vessel to half its original volume, it will cause the partial pressure of each gas to be doubled. So 1.20 becomes 2.40, and then 8.57 becomes 17.14. So these numbers in part B are now the new partial pressures at the moment that the stress or the disturbance occurred. Based on your answer to part B, let's calculate the value of Qp. So we have products over reactants, 17.14 squared divided by the product of 2.40 times 2.40, and interesting, the system actually remains at equilibrium because we just got a value of 51, so Q equals K. Now, if that's confusing, take a close look at the total number of moles of gas on the left. So we have 2 moles of reactants, 2 moles of gas on the left, and we have 2 moles of products, 2 moles of gas on the right. So normally when you decrease the volume of the reaction vessel for a gaseous equilibrium, it will shift to whichever side of the equation has a smaller number of moles of gaseous particles. But in this case, the reason why there was no shift in the equilibrium system at all as a response to this decrease in the reaction vessel is because there's an equal number of moles of gas on each side of the chemical equation. So no shift occurred and Q remains equal to K despite the decrease in the volume from 2 liters to 1 liter. So changes in the volume of the reaction vessel can cause a disturbance in a gaseous equilibrium system when there are different number of moles of gas on opposite sides of the chemical equation. But if there are the same number of moles of gas on the left as on the right, then there will not be a shift in response because Q will remain equal to K. So let's summarize what did happen in the situations where there was a shift. So if the volume of the reaction vessel for this gaseous system is decreased, the partial pressures of all gaseous species inside the vessel will increase. And if it can, the system will shift toward the side of the equation that has a lower number of moles of gaseous particles. It will try to alleviate the stress by decreasing the total pressure inside the reaction vessel. And if you go the other way, if the volume of the reaction vessel is increased, the partial pressures of all gaseous species will decrease, and the system will shift, if it can, toward the side of the equation that has a higher number of moles of gaseous particles. So it's going to try to respond to that stress by, if it can, increasing the total pressure inside the reaction vessel. All right, now this is question 14, something else to consider about a change in pressure. It says, If an inert, as in unreactive gas, such as helium or neon, is added to a gaseous system at equilibrium, the total pressure of the gas mixture increases. However, no shift in the equilibrium system will occur. Explain this result in terms of the reaction quotient Q or QP. So I'm going to go ahead and go back to that system that we had looked at earlier with 1 mole of N2O4 on the left and 2 moles of NO2 on the right. So we have a Kp that's 0.21 at 373 Kelvin, and I'm going to draw a particle diagram representing a mixture of N2O4 and NO2, and let's assume that we are already at equilibrium with this particle diagram. Now, if additional helium is added, I'm going to represent the helium particles in blue on this slide. Did the partial pressure of N2O4 change? And the answer is no. Did the partial pressure of NO2 change? Again, the answer is no. So even though the total pressure of the gas mixture was increased, helium is not part of the equilibrium system. It's not one of the reacting species. So the partial pressures of all of the reacting gaseous species, in this case, N2O4 and NO2, remain unchanged by the addition of helium. So Q remains equal to K. The system is still at equilibrium. So the answer to number 14 is that because Q was unchanged by the addition of this inert, unreactive gas, helium, the partial pressures of all of the reacting gaseous species remain unchanged. Q is still equal to K. No shift occurs because the system remains at equilibrium. Okay, now we're going to move on to question 15 in the packet. We're going to say goodbye to gaseous equilibrium systems, and we're going to talk about a different aqueous equilibrium system. And this particular system involving cobalt ions, this is one that I have demonstrated for you in class. So hopefully you find this particular system familiar from the demonstration that you saw in class. All right, here's question 15. Two different forms of the cobalt-2 ion are in equilibrium according to the equation shown above. A purple solution contains an equilibrium mixture of the pink cobalt H2O times 6 2 plus aqueous ion, colorless chloride ions, and blue cobalt Cl4 2 minus aqueous ion. So in part A, we have the reaction already represented by the equation above. We have to write the equilibrium constant expression, Kc, for the reaction shown above. So with Kc, that's concentration. We're going to use brackets. But remember that one of the chemicals in this equation is a liquid, and that's water. So solids and pure liquids are not included in the equilibrium constant expression. So we are not going to include the liquid H2O that you see on the right side of the equation. So we're still going to do products over reactants. So for this expression, it's going to be the concentration of that cobalt Cl4 2 minus aqueous ion on the top. On the bottom, it's going to be that cobalt H2O times 6 2 plus aqueous ion on the bottom. We also have chloride on the bottom, and because the chloride has a coefficient of 4, it's going to be the concentration of chloride raised to the 4th power. So that is our equilibrium constant expression, Kc. Again, we don't include liquid water because solids and liquids are not included. Now what we're going to do is take the equilibrium constant expression that we already wrote in part A, and we're going to do a substitution using some variables. And the variables are A, B, and C. So on the top, instead of writing the concentration of the CoCl4 2 minus ion, we're going to write the letter C. And on the bottom, instead of writing the cobalt H2O times 6 2 plus ion, we're going to write the letter A. And then for the chloride, it's going to be represented by the variable B, but it will still be raised to the 4th power. So the answer to part B is simply we've written the equilibrium constant expression, Kc, for this reaction, but we've used a substitution method in terms of these variables A, B, and C. All right, so far in this packet with respect to Le Chatelier's principle, we have seen the addition or removal of certain substances and how that affects the value of the reaction quotient Q. We've already seen examples where the volume of the reaction vessel for a gaseous system has been either decreased or increased. What we're going to take a look at now with this aqueous system is what happens when water is added. What happens when the system is diluted with water? So here we have a 10.0 milliliter sample of distilled water, and it was added to 10.0 milliliters of that purple solution that was already an equilibrium system. So we are disturbing the equilibrium by adding water to this aqueous system. So as a result of this dilution experiment, the color of the solution, which was purple, changed to pink. Part C, in which direction? Toward the left, reactants, or toward the right, products, did the equilibrium system shift as a result of the dilution with water? So it was purple and it changed to pink. And since that chemical is on the left, on the reactant side, that means that our answer to part C of this question is that the equilibrium system shifted toward the left, toward the reactants, and we can see that visually because of the change in color from purple to pink. But now we have to explain why that occurred. So I'm going to go ahead and do a Q versus K process here. Dilution of the purple solution with water caused the concentration of all aqueous species to decrease to half their original values. Use this information to write the expression for the reaction quotient, QC, in terms of the letters A, B, and C. So at the moment that water was added, all of the concentrations decreased by half. So here was our value of Kc. In terms of the letters, it's C divided by A times B to the fourth power. So watch what happens when all of these concentrations are decreased by half. I'm going to multiply each of these concentrations by half. Take a look. So now we have Q. We have 1/2 C on the top, we have 1/2 A on the bottom, and we have 1/2 B on the bottom. Now you can tell, based on simple mathematical procedures, that we have a 1/2 on the top and a 1/2 on the bottom, which I can cross out, which I just did, but there still is 1/2 raised to the fourth power on the bottom in this expression. So when I do some math here to realize that 1/2 raised to the fourth power would be 1/2 times 1/2 times 1/2 times 1/2, that's 1/16. My expression becomes C divided by the product of A times 1/16 B to the fourth power. Now when you divide by 1/16, that is the same as multiplying by 16. So take a look at this expression. QC equals 16 times C divided by the product of A times B to the fourth power. So let me go ahead and summarize what happened. Before the dilution with water, we had an equilibrium. And the equilibrium, in terms of these letters of the alphabet, these variables, is C over the product of A times B to the fourth power. But after the dilution, each of those aqueous ions had its concentration decreased to half its original value. And based on the math that we did, we came up with 16 times the value of K. So my point here is that the dilution caused Q to become larger than K. Hopefully you can see that that math works out, that Q is equal to 16 times the value of K, so Q becomes larger than K. And as you've already learned, when Q is larger than K, the equilibrium will shift toward the reactants as there is a net conversion from products to reactants. So the arrow of the direction of the shift would be from right to left, from products to reactants. And what happened? It turned pink, indicating that there was a net conversion from products to reactants. Now you might be wondering, is that always going to happen when you dilute an aqueous system with water? And the answer is it depends. Kind of like with gases, it depends on the number of moles of gas on each side of the equation. With aqueous systems, if you dilute it, it depends on how many aqueous particles you have on each side of the equation. So let me summarize what happened. When an aqueous equilibrium system in general is diluted with water, the concentrations of all aqueous species decrease, as you saw. The system will shift to whichever side of the equation has a higher number of moles of aqueous particles. So in this case, remember that water is not included in this equilibrium expression. So we have 5 moles of aqueous particles on the left. We have 1 mole, again, not counting the water, we have 1 mole of aqueous particles on the right. So what happened in this particular example is that dilution with water resulted in a shift toward the side of the equation with a higher number of moles of aqueous particles. And because that happened to be on the left side of the equation, the equilibrium system did shift toward the side of the equation that had a greater number of moles of aqueous particles. So that explains why it turned pink as a result of the dilution with water. So the last thing to consider in terms of the Le Chatelier's principle changes that we haven't seen so far in this packet is a change in temperature. So again, if you saw this demonstration in class, you remember that what I did is I took 1 purple test tube and I placed it in a beaker of hot water. I took another purple test tube and placed that in a beaker of ice water. So the purple solution contains an equilibrium of the pink cobalt H2O ion and colorless chloride and the blue cobalt Cl4 ion. So 1 test tube was placed in a hot water bath and the color changes from purple to blue. 1 test tube is kept at room temperature and the color remains purple. 1 test tube is placed in an ice water bath and the color changes from purple to pink. This is question 16, kind of summarizing the temperature change for this cobalt equilibrium system. Part A, in which direction, toward the left, reactants, or toward the right, products, did the equilibrium system shift as a result of placing the test tube in the hot water bath? Well, because it turned blue in the hot water bath, that means that it shifted toward the right or toward the products. Part B, in which direction, toward the left, reactants, or toward the right, products, did the equilibrium system shift as a result of placing the test tube in the ice water bath? When placed in the ice water bath, it turned pink, so therefore that represents a shift toward the left or toward the reactants. Part C, is the reaction represented by the equation shown above classified as endothermic or exothermic? Now, you might not be sure how to figure that out, so I'm going to tell you it is endothermic, but let's go ahead and take a look at why. So when the temperature of the system was increased, you can think of this as adding more heat to the test tube. So what happened is that the equilibrium system shifted toward the right, turning blue. In general, increasing the temperature will shift the equilibrium in the direction of the endothermic process that absorbs heat energy. And then the reverse. When the temperature of the system was decreased, it's like you're removing heat and it turned pink. Decreasing the temperature in general will shift the equilibrium in the direction of the exothermic process that releases heat energy. So the forward reaction from left to right is endothermic. So when the temperature was increased, it turned blue in the endothermic direction. And the reverse reaction is exothermic. So when the temperature is decreased, it shifted in the exothermic direction and turned pink. So number 16, part C, the answer is endothermic, as in the reaction as written from left to right is endothermic. All right, let me summarize temperature changes. If the temperature of an equilibrium system is increased, the system will shift in the direction of the endothermic process. If the temperature of an equilibrium system is decreased, the system will shift in the direction of the exothermic process. And unlike all of the other changes we've talked about so far, temperature is special. Temperature is unique in that when you change the temperature, you will actually cause the value of the equilibrium constant K to change. No other changes will result in a change in the value of K, but temperature changes will cause a change in the value of K. So how does the value of K change? Well, if the temperature change will cause a shift toward the right, toward the products, then the value of K will increase. On the other hand, if a temperature change will cause a shift toward the left, toward the reactants, then the value of K will decrease. But only changes in temperature will cause the value of K to change at all. Now, we are on the last page of this packet, and it's a rather long table. This is a summary of Le Chatelier's principle. Assume constant temperature unless specified. So we'll take a look at various stresses imposed on the equilibrium system. We'll see what effect that stress has on the Q versus K relationship, and then how the equilibrium system will respond to the stress. The value of K is not going to change unless the temperature is changed. Okay, our first example. What if you add a catalyst to speed up the reaction? As a result, Q remains equal to K. No shift in the equilibrium system occurs, but what happens is the system will simply reach equilibrium at a faster rate. What if additional reactant is added, not including solids or pure liquids? That will cause Q to become less than K, and as a result, the system will shift toward the right, toward the products. What if additional product is added, not including solids or pure liquids? As a result, Q becomes greater than K, and the system will shift toward the left, toward the reactants. What if some of the reactant is removed? Again, not including solids or pure liquids. Now Q becomes greater than K. The system shifts toward the left, toward the reactants. What if some of the product is removed? Again, not including solids or pure liquids. Q becomes less than K. The system will shift toward the right, toward the products. Now, if additional solid is added, or some of the solid is removed, Q remains equal to K. No shift occurs because the concentrations and partial pressures of all species are unchanged. What if an aqueous system is diluted with water? Well, how Q is affected, results may vary, but what happens is when you dilute an aqueous system with water, the concentrations of all aqueous species decrease, and the system will shift toward whichever side of the equation has a higher number of moles of aqueous particles. What if you have a gaseous equilibrium system and the volume of the reaction vessel is decreased? Again, how that affects Q versus K, results may vary, but the partial pressures of all gaseous species increase. The system will shift toward whichever side of the equation has a lower number of moles of gaseous particles. What if you have a gaseous equilibrium system and the volume of the reaction vessel is increased? Again, how it affects Q versus K, results may vary, but the partial pressures of all gaseous species decrease. The system will shift toward whichever side of the equation has a higher number of moles of gaseous particles. What if you add an inert gas, such as helium, to the equilibrium system? For a gaseous equilibrium system, Q remains equal to K. No shift occurs. The partial pressures of all reacting gaseous species are unchanged. Okay, now we come to this part of the table where the temperature is changing and it will affect the value of the equilibrium constant K. So let's first consider what happens if the temperature of the system is increased. So, if you have an endothermic reaction, it absorbs heat energy. So when the temperature of the system is increased, you can think of this as you're adding heat to the system. So an endothermic reaction will shift toward the right, toward the products, and as a result, the value of K increases. On the other hand, if you have an exothermic reaction, which releases heat energy, if the temperature of the system is increased, again, it's like you're adding heat energy to the system, an exothermic reaction will shift toward the left, toward the reactants, and as a result, the value of K decreases. Okay, so those are the changes when the temperature of the system is increased. Now let's take a look at what happens when the temperature of the system is decreased. This is like you're removing heat energy from the system. So if you have an endothermic reaction which absorbs heat energy, if the temperature of the system is decreased, like you're removing heat energy, an endothermic reaction will shift toward the left, toward the reactants, and as a result, the value of K decreases. If instead you have an exothermic reaction which releases heat energy, if you lower the temperature of the system, it's like you're removing heat energy. An exothermic reaction will shift toward the right, toward the products, and as a result, the value of K increases. All right, well, that's it. We have now reached the end of this packet. Therefore, this is the end of the video. I hope that you found all of these answers and explanations helpful. Thanks for watching.